And now that's your turn, Petr.
Okay, so thank you very much. So I would like to welcome everybody here on our seminar. So our speaker for today is Guchuan from the University of Michigan, and he will, as you can see, he will talk about the real cobordism theory and in general about Kervaire invariant one problem. So please, the Zoom is yours.
Yeah, thank you. Yeah, thank you for the introduction. Yeah, thank you for the invitation. It's really my pleasure to have the chance to speak here. Yeah, so the plan is I will start with some background like about the stable homotopy theory. And since I use this like iPad, so I can write simultaneously. So feel free to stop me, like say if the speed is too slow or you want to speed up, just let me know. So it's very easily like we can do a very similar to the chalkboard talk version. So as the title suggests, so I will first review how does the real cobordism theory, which is a generalized cohomology theory, and plays a crucial role in a recent breakthrough that Hopkins Ravenel solved the Kervaire invariant one problem. So this one has led to many further developments in the area of algebra topology, in particularly in equivariant and chromatic homotopy theory. So we'll also briefly review what happened after the new computation. In the last, I will talk joint work with Paul Hu, Igor Kriz, Petr, and Foling Zou, like on an attempt to make this story like now everything is only at prime 2, and we will give a proposed construction. This is an ongoing project for the all primes, so that the story can work for all primes. In particular, this may shed light on the 3 primary Kervaire invariant one problem. So the last part is based on a new computation, which has been done by Hu, Kriz, Somberg, and Zou. That one is on the archive available. But what I talk today is still in progress, and hopefully we'll see that soon. Okay. So maybe let's start with some background. Just let me know if this is boring, if I bored everyone, so we can speed up at any time.
This is fine with you on, so looks good. Looks good.
Okay, great. So so the background, like let's start with the stable homotopy theory, and maybe like usually you start with a new concept. It's always good to drop some of the adjectives. Let's start with the homotopy theory. So basically, it's just saying like let's study the geometrical object. But like let's only consider the basic topology. So it's topological spaces and continuous maps. But we can only consider them up to homotopy. So this is an equivalence relation between continuous maps. We see 2 maps, they're homotopy to each other. If one can continuously deform into the other one. So like mathematically, you can make this rigorous by introduce a parameter. Say like the parameter goes from time 0 to 1, and from 0, like the map looks like exactly the starting map, and like at the time goes to 1, it deformed into another map. And so we see so this introduces a relation like in the category of the morphisms. So you have a equivalence for the objects. So if 2 objects are equivalents in the homotopy sense, if there's an inverse map, such that the compositions are equivalent to the identity map. So some examples, seeing this is the classification. This is a much rough classification for the topological spaces. For example, if you think of the disk, that the solid disk in any dimension, you can think there is a like intuitively there's a deformation. You can shrink the radians, so it gets smaller and smaller and becomes 1 point. So in that sense, you can see this is actually like for any dimension, it's the same to the trivial one. So in that sense, this may not be detected very carefully, because like dimension is not an invariant anymore up to homotopy. However, it's still interesting because see the process, I just shrink. So if I dig a hole inside, this becomes a sphere. Then each dimension n, they're actually different from each other when the dimension are not the same. And so this may, so you may wonder like how to detect all this homotopy equivalence and so on. And at the subject, the name is called algebraic topology. So you always want to use some algebra invariance to detect these topological properties. And in this case, we study the homotopy groups. So like in the category, so you care about the morphisms between two objects. So in this case, as we said, it's continuous maps from X to Y. And the modular the relation, the homotopy equivalence. And if you replace the source by some basic objects, as we just give the examples, all the spheres are different. And there are some basic building blocks for all the other spaces. And then this becomes a group, has more algebraic structures on it. Like when n is greater or equal than 2, this is abelian groups. So this is called homotopy groups for each dimension n. And the n is just denotes the source is the n-dimensional spheres. So this is a nice invariant because Whitehead theorem told us for nice spaces, for example, if there are CW complexes, means that you can glue them piece by piece. So there are some simplicial objects. And for nice spaces, if a map induces isomorphisms on all these algebraic gadget, like the homotopy groups, then this map actually is a homotopy equivalence. So it's much easier to check on algebra that is isomorphic as a group or as a set than like just like construct an inverse map. However, like even you replace the target Y by some basic spaces like the spheres, the group is very hard. It's now known even now, and it's believed this is too complicated to be computed entirely within near future. So maybe I took a picture, a table from the Wikipedia page. As you can see, as the number goes larger and larger, so this part is the horizontal one is the source, the dimension of the source. So pi1 is S1, pi2 is S2. You're starting from a certain dimension of sphere. And this is a target. You map into S0, S1, S2. As you can see, when the number is large, the group just got more and more crazy. Like initial, like seems very easy, but later on, the number is getting larger and larger, and there are not much patterns going on. So it's a very hard subject to study. But at least there is some pattern. You see that each diagonally, eventually the group does not change anymore. So then this one leads to an observation that leads to the stable homotopy theory. So now we can add the additive stable back. So this one goes back like very earlier. It's essentially from the Friedenthal suspension theorem, which tells you that when your spaces are connective, highly connective, so when you suspension one time, you make the double mapping cone. So to increase the dimension, like the maps up to homotopy will not change. In particularly in this special case, it's saying if I'm thinking of the homotopy groups of spheres, like the only thing matters is the difference between the dimension. When n is large, so Sn is highly connective, is n connective or n minus 1 connective, depends on the definition for the word. And then like the group will not change. So I can make a definition for the stable homotopy group of spheres. So I only compute the group when it's stabilized. So this is a partial information of the whole information. So that's supposed to be slightly easier. So that's a part we will start with. But still, this has a very rich information. This can, of course, this cannot be computed entirely for now. And there's a reason for that one, because since the definition maybe seems very easy, but it contains rich information. So maybe let's mention two examples. First one is a cobordism. So this is how Petr started to compute these groups. So this is actually the group isomorphic to cobordism classes of stably framed K manifolds in the same dimension K. So instead of going into the details of this one, maybe let me just show the pictures and try to construct a map from one set to the other to convince you these two things can be related. So on one side, it's the stable homotopy groups of sphere. So by our definition, this is some sphere maps into another sphere with the difference of dimension K, and n is large enough. The other side is saying the cobordism classes of manifolds. So maybe like one example will be, so if there is a higher one-dimensional higher manifold, such the boundary will be these two manifolds, then we say this one, U and V, like maybe this is V, this is U, and that they are cobordism to each other if there is a higher dimensional W there. So how does these two groups relate to each other? So we can think of starting with a map from the n plus k dimension sphere into n-dimensional sphere. You can pick up any 2 points on the target. So if it's a generic point, and remember this map is up to homotopy, so you can adjust it so that the map is transferred on those points. And the transversality will give the pre-image will be a k-dimensional manifold. So the pre-image of a point will be a k-dimensional manifold there. And as you can imagine, if I make a different choice of 2 points, make a different choice of the point, then because the Sn is connective, path connective, there's a path between them. And then you just you choose the path so that everything is transverse. So you leave everything above. Then that gives the cobordism between these two choices. So it's well defined from a map, from a map in the represents a homotopy class that gives you a class in the bordism ring. And actually they're isomorphic to each other. And this is how Petr started to compute this group. But this is very hard because if you use this geometric way, you will make mistakes in very early steps. And this Petr made a mistake, like maybe just in pi 1 or pi 2 very earlier. And nowadays, we can compute the homotopy groups by algebra approach. So that one gives you rich geometric information. And maybe a slightly more surprising example is about the smooth structures. Remember, like in the construction, we talk about continuous maps without smooth conjecture, and we even quotient homotopy relation. So it even has less information than the continuous map. But it actually, the group tells you something about the smooth structure. Maybe the shocking example is starting from Mueller. Like Mueller construct a exotic sphere that is 7-dimensional sphere, which is a smooth manifold that is not diffeomorphic to the standard 7 sphere in R8 with the standard smooth structure. And another example is Kervaire construct a 10-dimensional manifold that does not emit any smooth structure. And so like later on, together they compute the groups of all exotic smooth structures on n-dimensional spheres when n is large.
May I ask you, group of exotic n sphere, that you mean that homotopy group of the mapping of the exotic n sphere? What do we mean that the group of exotic n sphere?
Oh yeah, that's a very good question. So maybe let me give the group structures for this one. So you see the group.
Yeah.
So the elements. So this group, like all the elements is smooth structures on n-dimensional sphere. So and what's a group structure? So I can use connective sum. So
Yeah.
this one topologically as a topological space is still Sn. However, like this two has different smooth structure in the group. So the connective one will also make it into a smooth sphere. And this one, like, so each of them is an element in here because it presents a smooth structure. And
so
this
that
is
only a hard group because it have the addition, but you don't have
yes, this you also
monoid.
At the inverse. But if you
Inverse also inverse.
So if you don't like ask strictly for the orientation, then adding itself will give the inverse.
Okay, thanks.
And so right, so that's a very good question. So this is how the group structure assigned to these smooth structures, and they actually compute this group in terms of the stable homotopy groups of sphere and a Kervaire invariant. And the Kervaire invariant is like developed by or like it's defined by Kervaire like for the first time, like to study for the construction of the 10 manifolds without smooth structure. And so in particularly in that paper, they also compute the case for the 7-dimensional sphere. Like Müller give one example of exotic one. Later they compute there in total 28 of them. And this is coming from the computations for a stable homotopy group of spheres. And the other piece, the Kervaire invariant, which originally defined just from the like framed manifold, actually also closely related to the stable homotopy group of spheres. So this is also a theorem by Broder around that time, so like 1970s. So the theorem says smooth manifolds, framed manifolds with Kervaire invariant 1 exist if and only if certain classes in the stable homotopy groups of spheres survives. In particular, these elements lives in certain dimension. It's only of the format 2 to the j plus 2 minus 2. So that implies the smooth manifolds with Kervaire invariant 1 could only lies in those dimensions. In particular, you can say 10 is not one of the choices. So Kervaire construct a topological manifold with Kervaire invariant 1 at dimension 10, so that cannot admit any smooth structure. Okay. So from there, we say that maybe stable homotopy groups of sphere is an interesting object, or it had rich information we would love to understand. And since we are moving to the stable world, we want to make our objects, morph them all stable. So in each time, we don't want to say I'm working with a space with high connectivity and so on. That's like in nowadays, like we work with the stable spaces, which called spectra in the homotopy in the algebraic topology, or like for a single one is a spectra. But this is it's different from the spectra in analysis. So this is a stable spaces. So in particularly, like in this talk, there are several different versions for it. So in this talk, we'll stick with the omega spectra. In the sense, well, you can imagine this is a stable space. So in each dimension, you have a spaces, and they're related to each other. So in this case, it's saying for each natural number, you have a spaces, and with the structure map, identify the next one with the previous one up to a loop. So this omega is a loop. So this is from S1 into Xn plus 1. And like everything is spaced. So the mapping spaces, the map between two topological spaces, you can make it into a space. So as you can imagine, so this from the map from S1 into Xn plus 1, this is also a space. And this one should be the same as up to homotopy should be the same as the previous one. And this is a sequence of all the information you need. So there are several motivations for this one, and maybe let me mention like one that may be most helpful for this talk is a spectra by the Brown representability theorem. It just represents a generalized cohomology theory. So this is also one motivation why you wanna introduce such object to work with stable space. So for example, if you work with the ordinary cohomology theory with FP coefficients. So this one can be regarded as you computing the homotopy groups of the function spectra from your space X into this spectra, Ellenberg-Magellan spectra HFP. So maybe it's more familiar to state the same results in spaces. So for each dimension n, there is a Ellenberg-Magellan spaces with the property there's only one non-trivial homotopy groups at dimension n as a FP or Z mod P at the group. So there exists such spaces, and this spaces has a property if you compute all the maps up to homotopy into this one, that gives you n-dimensional cohomology of your spaces. That's how they represent the ordinary cohomology. And here, similarly, now with this idea, like any generalized cohomology theory satisfies the axioms can be represented by a spectra. Maybe some interesting ones like will appear in later talks. In this talk is the complex K theory and the complex cobordism theory, which denoted by Ku and Mu. So for the Ku, the space is also very concrete. It's just like the classify spaces for the unit group or unitary group. So I only write two of them because from the Bott periodicity theorem is two periodic. So you can imagine the cohomology is two periodic. So the spaces present them is also two periodic. So you can just repeat Z times Bu and U, and then it repeats all the time. So this sequence of spaces gives a cohomology theory that represents the complex K theory, and together they form a spectra called Ku. And for the complex cobordism theory, you can also think this way. So thinking the above to give consider structure maps. So up to homotopy, if you know there's a one space X0, you know X1, X2, and so on. But there is something special for X0. X0 it's loop of X1, so it's loop twice of X2, and so on. So it can be looped up to n to Xn. So it's an infinite loop spaces in this case. And so by the cobordism, by Thom's thesis, you know, to compute the cobordism classes, you need to compute the homotopy or homology of a Thom spectral or Thom space. So it's actually the construction of Thom space is a good source for infinite loop spaces. So Mu is Thom spaces for the universal bundle over the unitary group, and then it's a infinite loop spaces. You can deloop all the time and give a spectrum in this case. Okay, so with all this clear setup, I think though it's time to state some big theorems that happens recently. So before, the Kervaire invariance one, we know that there are theta j lies in the certain dimension. It's 2j plus 2 minus 2. The question to ask whether such manifold exists or not has been converted to a question, to a homotopy question, whether this homotopy class survive or not. Do they exist in the stable homotopy group of spheres? As we know, the current computation limit is very limited. So you cannot just compute stem by stem and tell the answer. So the new big breakthrough is in 2009, and the paper is published in 2016. Here, Hopkins Ravenel proved they solved this 45 years conjecture and show that all the Kervaire invariant elements do not exist after starting from 7. And so there's only one remaining open case. It's theta 6 in 126, which the fate currently is now known. For the previous one, we know they do exist, either by construction or computation. And as we said before, this one gives many applications in geometric topology So for example, this told us, except in these 6 exceptional dimensions, every stably framed smooth manifold is actually framed cobordism to a sphere. So there's nothing else interesting. It's all of them are spheres except those 6. And so I wanna just briefly outline their proof and say that where does the real Bordism theory MUR plays a crucial role in the proof. So what they did is they formed the Bordism theory, the real one, MUR, which is just a complex one, but now you treat it not as a space, but a equivariant space or equivariant spectrum. So you consider this object together with the C2 action or D-mod2 action coming from the complex conjugation. So this has been extensively studied by Igor Kriz in 2001. From there, here, Hopkins Ravenel can construct a ring spectrum. It's a ring object in the category of spectrum. And so this new spectrum has the following properties. First one, this one detects the desired elements. So that is saying this is a ring. So you have a unit map from, so maybe in here in the spectrum category, the unit is just a sphere spectrum because the sphere tensor itself remains as a sphere. And there's a unit map from the sphere to this ring spectrum. And through this map, you can see the fate of those theta j. In particularly, if theta j exists in the sphere, then it will also survive and give non-trivial elements after in the omega part. So the omega does detect those theta j. And then they compute. So omega is much easier than the sphere. First, just like about periodicity, this one also periodic. It's 256 periodic. And in particularly, they can show the pi minus 2. So this is not a it's periodic, so it's not a connective one. So it's just like in the K theory, you invert the bot element, so you got the negative part of homotopy groups. So in particular, they show that pi minus 2 is trivial. In particular, for all those theta j lies in the dimension, the omega just vanishes. So you cannot detect anything interesting. That force the elements in the sphere has to be trivial too. And because the periodicity is 256, so the first time is 254 that the theta 7 lies in and all the rest, but not theta 6. So it's now known. That's the reason why there's an open case lies in there. And so this proof looks very easy because all the hard part is construct this omega and study the property of it. So the construction, here is a formula for it. Maybe it looks very complicated, but let me try to unpack it a little bit. So try to make sense of these notations. So you started with the real Bordism theory. So this MUR, that's a C2, the D-mod2 equivariant spectrum. The action is a complex conjugation. And this is a Hopkins Ravenel multiplicative norm functor. So it sends a D-mod2 spectrum to a D-mod8 spectrum. And so the way they send it is you start from X, you're gonna 4 copies of X smashed together. So it's also called multiplicative transfer. So maybe the analog in algebra is from a small group, you can, in group cohomology, from a small group, you can transfer to elements in the larger group just by making it at an orbit. And if you start with the coefficients, not just a module, but also has a ring structure, you can also multiply orbit together to get some fixed part. And the idea, this is a topological version of the idea. So you just D-mod8, quotient D-mod2, there are 4 elements in the co-site, and you just times 4 copies of X start together. So the C8 action is transfer those one by the co-set of the index and has a C2 action on each of this X. So this gives a C8 spectrum. And then you just invert something. So algebraically, you do some localization. And so as you can imagine, if you invert some element, that probably introduce periodicity. Like the K theory, you invert both element, you have the two periodic. And then after all these constructions, you take the Z mod 8 fixed point, and that will give this one. Maybe the analog is, if you just do the complex K theory KU, everything is torsion free. It doesn't say much of the homotopy group of spheres because everything is torsion. However, you take the C2 fixed point, it became the real K theory. And say the first half element in the dimension 1 and square of it in dimension 2. So here is a similar idea. So I take the Z mod 8 action that will capture some torsion elements, and in particularly that will be good enough to capture this Kervaire invariant 1 element. But still, maybe you have the question like why the real cobordism theory MUR plays a role. Like how do they have this one in mind? Like why this can capture this is the right one to capture the element. So I just copy one sentence from the response from the Dr. Ravenel, like when they received the Wambler Prize last year. So he described the project like feel like hiking in the Alpines only to find the shortcut up Mountain Everest. So the Mountain Everest refers to their solution to the Kervaire invariant 1 problem. But they're starting with a different problem, which the Alpines refers to, and that has a background starting from the chromatic homotopy theory. So maybe let me just briefly introduce chromatic homotopy theory and see how from there they start this project. They start to think of this object. So like the stable homotopy group sphere, like we said, we emphasized many times, is very hard to understand, but we do have some like results, very nice results, like starting back to Serre. Serre proved that the stable one, like in the positive dimensions, are all finite subgroups, finite abelian groups. And he proved this one like using the idea to localize. So he dealt with prime P part, like P torsion part each time. And so he can show this result. So this local to global idea can be extended by the chromatic homotopy theory. So it's just saying like for the P local case, maybe the P local sphere is still very hard to compute. So what we can do is the chromatic homotopy theory provide a framework. So we can further localize this P local sphere into smaller pieces, and with more structure, they're somehow periodic in some sense. In the like slightly more precise is just like the chromatic homotopy theory as a black box provides you for each prime P, for each natural number N, they provides you a very nice cohomology theory called the Morava E theory En, and there's a nice operation action on it. It's given by a group called the Morava stabilizer group. And the story generalizes the Adams operations on the complex K theory. Like that one construction like involves vector bundles and like very specific, and the framework can generalize to all height. And then the theory En with the action captures interesting information. Indeed, like all the information can be assembling property from the fixed point, like under this operation for En. Like if you can do for all primes, all heights, then you essentially have all the information you need. You can just recover the original one. So like then this interesting generalized cohomology and action actually comes from a deep connection between the formal group laws and the complex cobordism theory. This is a like theorem due to Quillen. And so maybe due to time reason, let's not unpack it, but you see the name, the complex cobordism theorem appears. So that's why this is a crucial object, because actually the theorem is basically saying the complex cobordism theorem is a universal one to all this nice generalized cohomology theory, which is known as the complex oriented cohomology series. All this En can be constructed from this MU. So the Alpons in the sentence just refers, they started with the idea to study ENHG for some finite group G in Gn, because Gn is very large, maybe it's hard to understand for now, but you can start with some finite subgroup, and this is reasonable, and at the height 1, prime 2, this is saying maybe directly study all the G, image of G part in the sphere is hard. It's a hard question, but I can start with from the complex case theory. First, take the C2 fixed point, got the real one. As we mentioned, this already sees more elements. This is the first hop elements, and they just using the same ideas, and they were trying to study this one. And actually, what they did is their detection spectra is essentially at height 4 and taking a larger group, theta 8. This is essentially like why they constructed in that way. So you start, En is from Mu, and so from Mu you got a map to En, and you just make it into a C2 equivalent map, just normal map Mu to C2 equivalent case, and then you invert certain element and essentially recover this one. So like in 2001, like Hu and Kriz extensively studied MUR, like the real cobordism theorem, and they observed that the complex orientation from Mu to construct En, this one should be also can be refined to a C2 Z-mod 2 equivalent map. That's saying like you can equip the complex conjugation on the left-hand side, and on the right-hand side you can equip with the inverse of the formal group, like the inverse in the group map, and this will be a C2 equivalent map at prime 2, and this is like later after the Hill Hopkins Ravenel story, like two students of Mike Hopkins, like Jeremy Han and Danny Shi, had the next paper real orientation, like explain this one in more detail and more general case, like seeing there is a C2 equivalent map from the MUR to the two other En. So that relates one side is the equivalent side, the other one is chromatic, like crucial players. And also in the 2001 paper, like Kriz also computed like MUR, the homotopy groups for it, and even for the RO Z-mod 2 grading, like with the representation grading homotopy groups. So for this one, they compute all the ENHC2 in the chromatic side for all heights, and their computation like agrees with HHR's computation later in their paper solved the Kervaire invariant 1 problem. Indeed, actually, the two spectral sequences are up to a re-index, they're isomorphic to each other. Essentially, it's the same information for the Z-mod 2 case. So in a joint work with Xiaolin Dannish, Guozhen Wang, and Zhou Lixu, we make precise of the isomorphism and using that one to improve the detection theorem, saying like even before taking the Z-mod 8 fixed point, just take the Z-mod 2 fixed point. We already detect the Kervaire invariant elements in there, and captures more elements from the spheres. Okay, so then so this explains why the construction of the omega makes sense. So maybe there's something more. There are new equivariant techniques that really helps the new computations. Like just as we mentioned, like from knowing the equivariant Z-mod 2 sinular algebra, like Kriz computed the homotopy groups for the C2 fixed point for all ENHC2, or in other words, they compute the homotopy groups for MUR. And this can also be done from studying the geometric fixed point. So later on, like in the HHR solution, what's new is they consider this multiplicative norm. That one gives us structure maps from the smaller groups to the larger groups. So if I want to study the Z-mod 8, I can study the subgroup Z-mod 2 first, and there are structure maps between them. And in addition to the classical restriction and the transfer map, now there is a multiplicative transfer called the norm map. Together with all this one, they're rigid enough, so I can have enough information for it. In particular, they show is 256 periodic. they also invited a new slice spectral sequences, the slice spectral sequences, which is more rigid, like on the E2 page than previous one. So in particularly from the starting algebraic input data, the E2 page, they already know the -2 stem has to be trivial. Before computing any differentials, do any topological computation, just the algebraic group computation, like it's good enough to show the vanish for the dimension. And that's all the key pieces, like, allow them to solve the conjecture. So in the last part, I want to mention something we are doing right now. And so as we say, we advertise the chromatic homotopy theory, saying we can assemble all the EN, and we will know for all primes, for all height, we will recover the stable homotopy group of spheres. And all the stories I told like before, like currently everything is just for prime 2. And so in another word, we don't have the all prime computation except the first case for height p-1. And there's not much new computation happening in chromatic side for the alt primes. And the reason is all the previous one, like, as you can see, the crucial player is MUR, it's a real cobordism theorem. It gives you the initial data like the C2, DEMO2 fixed point computation. So that one can be done because it has a very good geometric model. It's a complex conjugation, like C over R. You take the C2, you take the fixed point of the complex conjugation, you get the real number. However, for other alt primes, you care about the DEMO P action. And the DEMO P cannot be realized as a Galois group, like for a finite field extension, like something like C over R. So you do not have the geometric model like this one. So the classical, the MU, the complex cobordism theory, there's no DEMO P actions other than prime 2. So however, here Hopkins Ravenel has some conjectured construction like from their multiplicative norm. So they conjectured, so I can smash p-1 copies of MU together. There is a DEMO P action, and at prime 2, so I only need 1 copy of it. And they give some attempts. They even have a archive notes, which is unpublished. It's an archive paper saying how this would solve the 3 primary Kervaire invariant 1 problem. And later on, students and the postdocs at Harvard and MIT, like Jeremy Han, Andy Singer, and Dylan Wilson, they try to extend this idea, and they have some results for the all prime analogues of real orientations. But still, we don't have anything like the alt prime at the DEMO P spectra like MUR for the prime 2 due to the lag. So there's no new computations before. And so here, I would like to advertise our attempts on this question, on this direction. We give a construction for candidates of this MUR in the alt prime case. And so the difficulty is we don't have the geometric model, so we will take an algebraic approach. So maybe like the first, we care about the prime P case. So we first localize to prime P. And the classically, and also as well as the C2 case, DEMO2 equivalent case for prime 2, the localization of MU splits into copies of suspensions of BP, which is another spectrum named after those Brown and Peterson who defined it first. And classically, how does Brown-Peterson find this spectrum? They don't start to just p-localize MU, or nowadays with the equivalence theorem, you can say every formal group law can be p-typicalized over ZP, can be p-typicalized. And you do the p-typicalization that gives you idempotent map, and the idempotent summand gives you BP from MU. But back to those days, Brown-Peterson just want to study if there is a spectrum with certain cohomology. The study started from the stimulus algebra, and they look at the evenly concentrated part. They found that's a subalgebra. And they were wondering if this can be realized as a homology of a spectrum or a space. And they found this can be realized, and the result is a Brown-Peterson spectrum. That's how they constructed it from the very beginning. And so similar story holds like the property for the cohomology of the BPR in the prime 2 case for the Z-mod-2 equivariant one is closely related to the Z-mod-2 equivariant stimulus algebra. And this is due to Guchuan and Kriz in the paper. And so our algebra approach is the following. So as I advertised from the beginning, very recently, Kriz, Petr, and sorry, like I should put the last names. Yeah, and the Foling Zou. So they compute the Z-mod-P equivariant dual stimulus algebra for all primes. And so although like maybe like most techniques would be similar to the prime 2 case, but this is a much harder computation. As previously, there are other groups study the same problem. In particularly, also like the Krishano, Sanker, and Dylan Wilson has a paper on this one. They point out this is harder than the prime 2 case, because as a HFP module, this is not free anymore. Like the HF2 smash HF2, classically, like all the generators are free. It's polynomial and the exterior algebra. And similarly, phenomena happens for prime 2 for Z-mod-2 equivariant case. However, at all prime case, if you smash 2 Allenberger-Magellan space together, whose homotopy groups is the stimulus algebra or dual stimulus algebra, it does not split as a direct sum of suspensions of those HFP. Even you introduce the RO-Z-mod-P suspension, it's still not enough. There are some interesting extensions between them. So the algebra is not free. There are interesting extension that matters, which makes the computation is much harder. But like, luckily, this is done like in great detail, very carefully by the group very recently. So our approach is based on this new computation. We recognize the analog part, the evenly concentrated part in the dual stimulus algebra, and we are trying to construct a Z-mod-P equivariant spectrum such that the homology of this one will realize the algebra we see in the new computation. And that's how we give a construction of the BPR, and this one compute, and also let's do a computation for the homotopy groups of it. And in particularly, in the large prime case, this will not be just P minus, will not coincide with the P minus 1 smash together of the copies of BP. So like the main result for us is we construct a Z-mod-P equivariant spectral BPR in the all prime case, and we can compute the homotopy groups for it. This one has the nice structures as conjectured by here Hopkins Ravenel. In particular, the Z-mod-P geometric fixed point is just HFP, and also like in the computation, the differential patterns looks exactly the same length as those differentials has been claimed and conjectured and stated like in many talks, like the differential patterns for those computations in chromatic homotopy theory with the Z-mod-P fixed points. So this leads to the future directions. Like we conjectured, there will also be a Z-mod-P equivariant map. That's all prime reorientation from our BPR for the all prime case to the EN, and this may lead to the new computations for the all prime case and give much more information for the stable homotopy group of spheres, and may shed light on important questions, including the 3 primary analog of the Kervaire invariant one. So that's like this part is still in progress, and we do have some evidence like from the construction and also from the formal group law point of view. Yeah, and yeah, I think that's all I have for today, and maybe we can have questions for the rest of time. And thank you very much for your patience.
Okay, so thank you very much to Guchuan for his nice introductory talk related to Kervaire invariant one problem. So it's time for questions or comments, or you might ask whatever you want related to this subject. So it's on you. So everybody can ask those questions.
Yeah, so I have a real naive question somehow related to the conjectures that we formulated in the end, so which appears in these future directions. So you conjecture the existence of such map, but like why, once again, like why do you believe that it should exist? Like what are the indications? Like what's
what's the evidence for the existence?
yeah,
It's
exactly.
the evidence for the existence, right?
Yeah, I think well, yes. So maybe I should be more precise. Like first, this n should be of the format. It's k times p minus 1 for certain heights, and the reason we pick up this height is this is from the formal group law side. Then this one will admit a Z mod P action. So both sides will be Z mod P covariance spectral. That makes sense. And as you can imagine, on one side, there is a formal group law, and you can make the Z mod P action to have many formal group laws. So that indicates that's also the reason why they conjecture there might be a P minus 1 copy of BP smashed together. Each of them gives one of the formal group law and the action gamma action on it, and then the gamma square X on it. And that's from the formal group law side. You want to have the map because the BP is a universal one for the P typical formal group law. So you want this one should be somehow in the universal one for the formal group law with ZP action in certain sense. So and that's like our evidence for it. And another evidence is just like the computationally, like the Z mod P fixed point, like the differential of the same length. So it's very likely they're closely related.
Thanks.
Yeah.
Okay, some other questions. Okay, so for example, I will ask one explicit question. So in the construction by, I mean, that norm map used by Hill and Ravenel and Hopkins. So there was that fourth wedge power of X. Yeah, it's in the bottom of the page. So my question is how the generator of Z over A, this finite group, how does it act on this on X wedge X wedge X wedge X?
Yes, so that's a very nice question. That's a very good question. Maybe let me just give the example norm to Z mod 4. So it's slightly easier, but the idea is the same. So this will have two copies of X, and like the action is somehow you want to send this one to minus X or Y bar. Y bar is the C2 action on Y, and that gives the Z mod 4 action of the generator. So you can go on, and this will change X to front and the Y bar to here, and then and then you'll go. So this is C2 action, so Y goes back to Y.
Y X bar.
Yeah, and then you do one more X Y.
And finally X Y again.
Yeah. So this is how you construct a Z mod 4 one for Z mod 2. But like this one, but be careful. You need extra structures because you need X. Oh, sorry. This one does not need extra structures. But if you want this one goes back to X as a Z mod 4 action, so you need to have a very nice multiplication of X.
Okay.
So this is an external norm construction. When your coefficients have a ring structure, you have an internal one. That one asks for higher structures. For the action, the multiplication has to be commute very well, and that what happens for the Morova E series side. Yeah, that's the reason why I just like changed the EN fixed point from Z mod to Z mod 8, but do not put extra 3 copies of EN in that case.
Okay. So another question is, you said something, you mentioned that in the dimension 1 to 6, it's not known, not decided. So what's the progress in this direction? So is it expected that what should happen? So is it completely open, or what people think about this case?
Yes, I think there are several groups like had worked on or has been working on this one. So maybe some of them is like there's some attempts like first like using this new technology. Like there's a paper by Hill, Danny Xiaolin Shi, Guo Zhenwang, and Zhou Lixu. They completely compute E4 HD mod 4. So they do not compute HD mod 8 entirely, but they were able to compute HD mod 4. That may be the first approximation, so that was an attempt. But then like the computation was already very hard. Like it's like the longest differential is D61. So and also there's another attempt, because this approach can only show it does not exist. So what happens if it exists? So I think there's also people like with the same first name as you, but like he's from Russian. Like he has some geometric method, and he has been studied the Kervaire invariant one element like for a long time. And there's some results in that direction, but which the approach is very different from this one. And so in addition to that one, there's also like, because there's new breakthrough in the computations for the stable homotopy group of spheres by stems. Previously, our knowledge is around 60, like 59 or 60 or something. But nowadays, modular very few differentials uncertainties is up to 90 or like even maybe 95 or something. So this is from the new motivic method conducted by Dan Eskson, Guo Zhenwang, and Zhou Lixu. And so they're trying to using the new machine computation for the algebra side and the new motivic strategy. They may want to push it even further. So maybe there are enough information around the range, which now is out of reach, but maybe there's a chance they can have more information if they push their method like really hard and determine the fate of 1 to 6. Yeah, that is some of the part of it. I'm sure like maybe there are more people thinking in more different ways, but yeah. Yeah, but I think like now maybe it's not believed that either exists or not exist. So it's as far as I know.
Yeah. Okay, thank you. So some other questions. One is usually if I'm quite curious about various
right, maybe also
structures and problems. So you might ask one if you are interested in something exotic. So it's the right time and right place.
Oh, yeah, so this is a name for the Russian.
Oh yes. So if there is no other question, seems to be. So we thank Guchuan again for his nice review lecture, and well, the seminar is over. Thank you very much.
Thank you for the invitation. And thank you for patience.
Yeah.
Yeah,
Thank you very much.
thank you.